We think we have a solid handle on gravity, one of the fundamental forces of the universe. But what if the whole picture is wrong? Today, we're going to explore a pretty radical new idea called the ZETA Framework. And it doesn't just tweak Einstein's theories. No, it proposes a completely different reality. And the wildest part, we might be able to test it right now.
I mean, look, Einstein's theory of general relativity is an absolute icon, a masterpiece. It describes gravity as the curvature of space-time. But for all its triumphs, it has this one giant, glaring problem. It just doesn't play nice with our other pillar of modern physics, quantum mechanics. So you've got this clash of titans right at the heart of modern physics. You have these two incredibly successful pictures of reality, and they just flat out contradict each other. They can't both be right. This is the crack that physicists are scrambling to fix, and it's forcing them to look for some seriously out there new ideas.
And this slide really gets to the core of the problem. On one hand, you have general relativity, which paints this picture of a smooth, continuous world, like a flowing river of spacetime. But then on the other hand, quantum mechanics says reality is, well, it's kind of pixelated, right? It's all about discrete packets of energy and probabilities. Trying to merge them is like trying to play a 4K Blu-ray on an old 8-bit Nintendo. The formats just don't match up.
Okay, so that's the setup, and this is where the ZETA framework walks onto the stage. And here's the thing you really gotta get. ZETA isn't just about tweaking the math. No, it's proposing a completely different story about what reality is even made of. Physicists call this its ontology.
All right, let's break it down, starting with time. In general relativity, you're taught that time is flexible, right? It can stretch, it can slow down. That's time dilation. ZETA's view, totally different. It says, nope, time is just a simple, rigid counter. Think of it like a universal metronome, ticking away at the exact same rate for everything, everywhere. It doesn't stretch, it doesn't bend, period.
Okay, what about space? So you know that classic image of Einstein's gravity, the bowling ball on the trampoline, right? That elastic sheet? Well, ZETA says forget it. Space isn't a trampoline, it's more like a rigid, fixed scaffolding. It's just the stage. The action doesn't happen to the stage.
Okay, so you're probably thinking, wait a minute, if time and space are rigid, then what the heck is gravity? And this slide, this is the most critical shift in thinking. The ZETA framework says all that elasticity, all that dynamic action, isn't in space-time at all. It's in matter. Matter is the only thing that's elastic. So all those wild effects we see, like clocks ticking slower near a planet, that's not time itself slowing down. It's the physical clock, the actual atoms, changing its internal ticking rate.
All right, so if we're throwing out curved space-time, how does gravity actually work? What's the mechanism? Well, ZETA proposes something it calls the law of communication. It reframes gravity as, well, as a conversation.
So here's the wild idea. Every single object in the universe, from one atom to an entire galaxy, is constantly broadcasting a signal. And at the same time, it's listening for the signals from everything else. It's this non-stop, two-way, universe-wide communication. And according to ZETA, that conversation, that is gravity.
And this quote, man, it just nails the concept. The gravitational broadcast is universal, but how an object receives that signal, how it hears the conversation, depends entirely on its own internal structure. It's not just about mass, it's about what you're made of. So let's really dig into this two-sided conversation. Step 1, the broadcast. This is universal. It's based on mass energy. And this is super important because it's why a feather and a bowling ball fall at the same rate, right? It keeps Einstein's equivalence principle for trajectories perfectly intact. But step 2, the reception, that's where all the new physics is hiding. How an object internally responds to that gravitational signal depends on its atoms, its chemical bonds, its quantum states. Basically, different materials are going to hear the same gravity message differently.
Okay, this is a really cool story, right? But is it actually science? Well, for any idea to be taken seriously, it has to make a prediction you can go out and test, and maybe even prove wrong. And that brings us to the big finale, a very specific, falsifiable experiment called the delta G test. So what exactly is this delta G? It's actually pretty simple. It's just a number that measures the tiny, tiny difference between what Einstein's theory predicts for a clock in a gravitational field and what a real-world clock, made of a specific material, actually does. We're literally looking for a new, material-dependent effect.
And here's what makes this such a clean test. General relativity's prediction is, well, it's about as simple as it gets. It's zero.
Because according to Einstein, gravity messes with time itself. So it shouldn't matter if your clock is made of atoms, or wood, or cheese. They should all slow down by the exact same amount. So the difference between any two of them, delta G, has to be 0. No exceptions. But ZETA throws down the gauntlet and says no way. It predicts delta G as not 0. Because in ZETA, the effect is happening to the matter. So the clock's internal atomic machinery really matters. Different types of atomic clocks should tick at slightly different rates. This is a direct head-to-head showdown with general relativity.
And it gets even better, because the prediction is incredibly specific. ZETA doesn't just say it's not 0. No, it predicts a precise ranking for our most advanced atomic clocks. It predicts that strontium lattice clocks, which have a really complex quantum structure, should show the biggest effect. Ytterbium somewhere in the middle, and then aluminum ion clocks, which are simpler, should show the smallest effect. This is a bold, risky prediction made before all the data is in.
So how do they get to that prediction? Well, this table basically shows the logical chain of reasoning. It all starts with that law of communication. From there, you get to a concept called spectral susceptibility. Fancy term, but it just means how sensitive a material is to gravity's broadcast. You add in some other real-world physics, like how quantum coherence can amplify the effect, and each step builds on the last until you arrive at the final testable prediction, that specific ordering for delta G.
Okay, so let's play this out. Let's say the experiments are run, and the results come in, and they find a non-zero delta G. What happens then? I mean, why is this one little number such a potential bombshell?
Finding a non-zero delta G would just be, well, revolutionary. For one, it would be the first ever signal we've ever detected in a lab from that mysterious border between gravity and quantum mechanics. It would prove that gravity isn't structure blind. It actually does care what things are made of. And maybe most importantly, it would show gravity can talk directly to the weirdest parts of the quantum world, which could unlock some of the deepest puzzles in all of physics, like the black hole information paradox.
And maybe the craziest part of all of this? This isn't some sci-fi dream that needs a galaxy-sized particle accelerator. No, we can test this, like right now, with the technology we already have. The question it's asking is actually pretty straightforward. Can gravity tell the difference between a messy, classical cloud of atoms and a perfectly ordered, quantum coherent state of those exact same atoms? ZETA says yes, and our atomic clocks are finally good enough to find out if it's right.
And that leaves us with this one final, really tantalizing thought. The little bit of data we have so far, and it's not statistically significant yet, I have to stress that, but it just so happens to line up with the ordering ZETA predicts. So the question is, are our most precise clocks on Earth already whispering the first hints of this hidden conversation between gravity and the quantum world? And have you just not been listening closely enough?